Scientists have identified the secret that fuels Yellowstone's explosive Hellfire. It's the prettiest powder keg on the planet, the Yellowstone supervolcano, simmering under the mystique and grandeur of the national park that adorns the fearsome caldera. And scientists just got one step closer to understanding the hidden geology of this epic blowhole. Using supercomputers to model the behavior of two known magma chambers concealed below the surface of Yellowstone, scientists have identified a transition zone where the magma bodies almost meet. Here, they form a vast slab of solidified, pressure-trapping rock that could be what fuels the supervolcano's hellish explosions. We think that this structure is what causes the rhyolite basalt volcanism throughout the Yellowstone hotspot, including supervolcanic eruptions, says geologist Ilya Bindeman from the University of Oregon. This is the nursery, a geological and petrological match with eruptive products. Bindeman and his team detected this naturally occurring munitions dump underground by running simulations based on recent research from scientists at the University of Utah, who used seismic imaging to detect not just one but two gargantuan magma chambers buried within the crust of Yellowstone caldera. To investigate how these dual chambers of molten rock came to be and to try to understand the magma transfer relationship between them, Bindeman and colleagues ran computer simulations tracing Yellowstone's hypothetical evolution over 7 million years, to see how these disparate chambers might form. The numbers suggest the seismic readings aren't wrong, with repeated simulations producing two magma chambers, separated by a transition zone made up of what's called a midcrustal sill composed of cooler magma, which is sandwiched between the hotter, more viscous reservoirs. Per the modeling, this rock shelf is located about 10 kilometers, 6.2 miles, below the surface of Yellowstone, and is between 10 to 15 kilometers, 9.3 miles, thick. The sill is composed of solidified gabbro, a rock formed from cooled magma, and the researchers say it's possible the same phenomenon forms in other supervolcanoes around the world. Due to the simulated basis of the study, we can only hypothesis about the midcrustal sill's existence for now, but given the data confirm seismic observations of the caldera, the team thinks their findings offer the first glimpse of how magma distributes itself inside the supervolcano. While these insights don't necessarily tell us any more about how or when Yellowstone might next erupt, it does bring us closer to that kind of understanding, and when we're talking about an event that could choke the planet in a catastrophic volcanic winter, that's some pretty important stuff to know.